Let's dive straight in. Number 8, the Venus question. For most of the last half-century, Venus was considered a closed case. We examined our planetary neighbor and found something resembling a vision of the apocalypse. Surface temperatures averaging around 900 degrees Fahrenheit, hot enough to liquefy lead. Atmospheric pressure 92 times greater than what we experience on Earth, equivalent to being submerged nearly a kilometer beneath the ocean. The cloud layers consist of concentrated sulfuric acid. When Soviet engineers dispatched their heavily reinforced Venera probes to the surface throughout the 1970s and 80s, those machines built to withstand punishment were crushed and incinerated within a single hour. So the broader scientific community largely moved on. The hunt for life in our solar system redirected itself toward the dusty plains of Mars and the subsurface oceans buried beneath the icy shells of Jupiter's and Saturn's moons. Venus became a warning, a geological tombstone, a textbook illustration of what a runaway greenhouse effect looks like when taken to its logical, catastrophic conclusion. Then September 2020 arrived, and with it, one of the most contested announcements in modern astronomy. An international research team, led by Professor Jane Greaves of Cardiff University, turned the James Clerk Maxwell Telescope in Hawaii and the ALMA Observatory in Chile toward the Venusian atmosphere, not the surface, but the temperate cloud layer approximately 30 miles above it, where, remarkably, pressure and temperature conditions are surprisingly close to those found at Earth's surface. And buried within the millimeter wavelength radio spectra, they identified the chemical fingerprint of a gas called phosphine. On Earth, phosphine, a molecule made of one phosphorus atom bonded to 3 hydrogen atoms, is extraordinarily rare and acutely toxic. More significantly, it carries a very particular biological implication. Here on our planet, phosphine arises from only 2 sources: industrial production in human laboratories, or the metabolic activity of anaerobic microbes living in oxygen-depleted environments, swamps, sediment, the intestinal systems of animals. Generating phosphine requires a significant energy input, forcing phosphorus and hydrogen together against considerable resistance. In Venus's highly oxidized atmosphere, any phosphine present should be destroyed almost immediately after forming. Its existence there makes no chemical sense. And yet the data pointed to concentrations of around 20 parts per billion. The implication was immediate and electrifying. Could microbial life have retreated upward into the Venusian cloud deck billions of years ago, as the surface became uninhabitable, evolving over geological time to survive suspended in droplets of sulfuric acid? Could we be looking at an aerial biosphere? The debate that followed was ferocious. Competing research teams rushed to re-examine the original data. Some argued the detection was a calibration artifact, a ghost in the telescope's signal processing. Others contended the signal had been misidentified and was actually sulfur dioxide, a compound that is genuinely abundant in that environment. A third camp proposed exotic geological or photochemical mechanisms, perhaps violent volcanic outgassing, injecting phosphorus compounds high into the atmosphere that might generate phosphine through entirely unknown pathways, no biology required. Years on, the argument has not been settled, but subsequent independent analyses have actually recovered a phosphine signal in archival data from NASA's Pioneer Venus mission dating back to 1978, a probe that directly sampled the Venusian atmosphere and whose readings had, for decades, gone unnoticed. Whether what we're detecting on Venus represents a novel and undiscovered chemical process or the first indirect signature of life beyond Earth, the discovery accomplished something important regardless. It broke our assumptions. It reminded us that the universe has no obligation to confine habitability to the environments we find comfortable, and that the most profound mysteries in the cosmos might be drifting in a toxic, acidic haze. Right next door. Number 7. Planetary defense becomes real. The night sky gives the impression of stillness. In reality, our solar system is littered with the remnants of planetary formation, millions of rocks hurtling through space at hypervelocity, following orbital paths that have existed since before the Earth had a crust. 66 million years ago, a single object the approximate size of Mount Everest struck the Yucatan Peninsula with the energy equivalent to 1 billion nuclear weapons, terminating the reign of the non-avian dinosaurs. They had no means of preventing it. Until very recently, neither did we. If astronomers had detected a civilization-ending asteroid on a confirmed collision course with Earth even 10 years ago, humanity would have possessed no verified method of deflection. That situation changed on the 26th of September, 2022. NASA's DART mission, the Double Asteroid Redirection Test, launched a spacecraft roughly the size of a vending machine toward a binary asteroid system located approximately 7 million miles from Earth. The system consisted of a larger body, Dimorphos, orbited by a 525-foot moonlet called Dimorphos. Neither posed any threat to our planet. They were chosen specifically as a test range. The goal was elegantly direct: strike the moonlet at 14,000 miles per hour and determine whether the kinetic force of the impact could produce a measurable change in its orbital period. What makes the engineering achievement genuinely extraordinary is the precision involved. DART had to navigate autonomously across millions of miles of empty space, identify a target that appeared as little more than a single pixel in its cameras until the final approach, and make real-time trajectory corrections at speeds where even a fraction of a second's delay would have meant a miss. As the live telemetry streamed back to mission control, images of Dimorphos resolved into breathtaking clarity, a rough, boulder-strewn surface. Not solid rock, but a loosely aggregated rubble pile held together by its own weak gravity. Individual stones were visible in the final frames. Then the feed cut to static. Impact confirmed. The collision displaced over 2 million pounds of rock and debris, blasting a plume of material tens of thousands of miles into space, and momentarily transforming the asteroid into something resembling a comet with a bright, glittering tail. But the true measure of success came in the following weeks, as Earth-based observatories tracked the orbital period of Dimorphos around Dimorphos. Before the impact, one full orbit took 11 hours and 55 minutes. NASA's threshold for mission success was a reduction of 73 seconds. The actual result, a reduction of 32 minutes. The significance of this moment extends well beyond the technical. For the first time in the 4-5 billion year history of this planet, a biological species reached into the solar system and deliberately altered the orbital mechanics of another body. We moved a world. If an asteroid ever locks its trajectory onto Earth, we now possess a proven, testable method of changing that outcome. We are no longer simply subject to the physics of the solar system. We are participants in it. Number 6. Material from the beginning of everything. Earth is, geologically speaking, a restless planet. Tectonic activity, liquid water, and a dynamic atmosphere have collectively erased the physical record of our world's earliest history. The rocks that witnessed the formation of the solar system no longer exist here. To find them, we have to look outward to the asteroids. These are the leftover building materials, the fragments that never accumulated into a planet, preserving within themselves the chemistry of the early solar system in essentially unaltered form. In September 2023, NASA's OSIRIS-REx mission completed a journey that returned the most scientifically valuable and primordial extraterrestrial material ever brought to Earth. The target was Bennu, a near-Earth asteroid shaped roughly like a spinning top, approximately as tall as the Empire State Building. Bennu is a carbonaceous asteroid, meaning it is chemically rich in carbon, the foundational element of all known biology. It is also classified as a potentially hazardous object, carrying a small but non-zero probability of impacting Earth sometime in the late 22nd century. OSIRIS-REx arrived at Bennu in 2018, and what the mission encountered immediately upended expectations. Pre-arrival modeling based on thermal data had suggested a relatively smooth, accessible surface, something like a gravelly beach. The first close-range imagery told a completely different story. Bennu was a chaotic landscape of jagged, overlapping boulders, with no open terrain suitable for a safe collection maneuver. The engineering team had to map the entire surface down to centimeter resolution just to identify a viable touchdown zone, a spot only a few meters across, ringed by house-sized rocks. The collection event in October 2020 provided yet another surprise. As the spacecraft's robotic arm made contact, the surface offered virtually no resistance. Rather than touching solid ground, the arm plunged nearly 20 inches into the asteroid because Bennu's outer layer is not consolidated rock, but an extraordinarily loose aggregate of gravel held together by almost nothing but microgravity. Had the spacecraft's thrusters not immediately fired to reverse the descent, a multi-billion-dollar probe would have been swallowed and buried inside an asteroid. It escaped, carrying with it a substantial cache of extraterrestrial material. On the 24th of September, 2023, the return capsule separated from the spacecraft entered Earth's atmosphere and came to rest softly in the Utah desert. When scientists opened the sample container in a clean room environment, what they found was extraordinary, even by the standards of the mission. Alongside carbon compounds and water-bearing clay minerals, the sample contained the chemical precursors to biological processes, including uracil, one of the nucleobases that constitutes RNA. It contained complex organic molecules formed before Earth itself existed. This single canister of material provides direct physical evidence in support of the panspermia hypothesis, the idea that the early Earth was essentially a sterile rock, and that the molecular toolkit required to initiate life was delivered from space by impacting bodies like Bennu. We may, in a very literal sense, be holding the origin of ourselves. Number 5. First flight on another world. Some breakthroughs are not about finding something new. They're about doing something that the governing physics of an environment makes extraordinarily difficult. When NASA's Perseverance rover touched down in Jezero Crater in February 2021, it carried attached beneath its belly a small piece of hardware, lightweight, fragile in appearance, looking almost like a camera drone. This was Ingenuity. The challenge of achieving powered flight on Mars is difficult to fully appreciate until you examine the numbers. Martian gravity is roughly 1/3 that of Earth, which helps. The atmosphere, however, is the fundamental obstacle. The Martian atmospheric density at the surface is approximately 1% of Earth's at sea level. Waving your hand through the Martian air, you would barely register any resistance. Aerodynamically, flying a helicopter on Mars is comparable to flying one on Earth at an altitude of 100,000 feet, more than twice the cruising altitude of commercial aircraft, at the boundary where the air begins to approximate a vacuum. To generate sufficient lift in those conditions, Ingenuity's carbon fiber rotor blades spanned 4 feet across and were required to spin at 2,500 revolutions per minute, roughly 5 times the rotor speed of a standard passenger helicopter. The vehicle also had to survive Martian nights during which temperatures dropped to around -130 degrees Fahrenheit, risking damage to both its delicate electronics and its battery systems. And because radio signals can take up to 20 minutes to travel between Earth and Mars, no remote piloting was possible. Ingenuity had to navigate autonomously, using onboard cameras and algorithms to interpret the terrain below and correct its own flight path in real time. On the 19th of April, 2021, Ingenuity spun up its rotors. It lifted clear of the rust-colored surface, climbed to roughly 10 feet, hovered in the alien atmosphere for 39 seconds, and returned to the ground intact. It was, without exaggeration, a Wright brothers moment. A small swatch of fabric from the original 1903 flyer was actually carried beneath Ingenuity's solar panel, a deliberate symbolic thread connecting humanity's first powered flight on Earth to its first on another world. Ingenuity had been designed as a technology demonstrator, with a mission plan of up to 5 flights over approximately 30 days. It ultimately flew 72 times before a rough landing caused rotor blade damage in early 2024. In the interim, it transitioned from experimental hardware into a functioning operational scout, mapping hazardous terrain ahead of Perseverance and identifying scientifically significant targets, including ancient river delta formations. The lesson is straightforward. We are no longer confined to driving slowly across the surfaces of other worlds. The skies of distant planets are accessible to us. Number 4, an ocean world with a biosignature hint. The search for exoplanets has, for decades, been fundamentally about one thing: finding liquid water. Not as an aesthetic preference, but because water appears to be the foundational solvent for all the chemistry that produces biology as we understand it. The habitable zone, the orbital range around a star where surface temperatures theoretically permit liquid water to exist, has been the primary focus of planet-hunting missions for this reason. In 2019, astronomers using the Hubble Space Telescope made a landmark detection. Their target was K2-18b, an exoplanet located approximately 124 light-years away in the constellation Leo. K2-18b is classified as a sub-Neptune or super-Earth, 2.6 times the radius of our planet and roughly 8.6 times its mass, and it orbits a red dwarf star squarely within the habitable zone. As the planet transited across its host star, starlight filtered through its atmosphere, and spectroscopic analysis of that light revealed an unambiguous signature of water vapor. This was the first confirmed detection of water in the atmosphere of a planet residing in a stellar habitable zone. But K2-18b is not a comfortable analog for Earth. Its mass implies surface gravity that would be crushing by any standard we're familiar with. Most models suggest it lacks a rocky surface entirely. Instead, current scientific thinking characterizes it as a Haitian world, a planet entirely covered by a global ocean potentially thousands of miles in depth, blanketed by a thick, hydrogen-dominated atmosphere. No continents, no shorelines, just an endless, lightless, pressurized ocean beneath a sky lit by the dim red glow of a distant dwarf star, at pressures that would collapse any submarine we could currently design. What makes this category of world particularly significant is thermal. Hydrogen-rich atmospheres act as powerful thermal insulators, meaning Haitian worlds may remain viable for liquid water at orbital distances far greater than Earth analog planets could tolerate. And statistically, this class of planet is among the most common we detect in the galaxy. More recently, the James Webb Space Telescope turned its instruments toward K2-18b and identified carbon-bearing molecules, including methane and carbon dioxide. But perhaps more unsettling, a tentative, weak signal from a molecule called dimethyl sulfide. On Earth, dimethyl sulfide is produced exclusively by living organisms, specifically by marine phytoplankton. The signal has not yet been confirmed, and the data is still undergoing verification. But consider the implication. The first evidence of biology elsewhere in the universe might not come from a green, rocky, sunlit world. It may come from something blind and strange, drifting in the lightless, pressurized depths of an ocean with no bottom. Number 3, a visitor from another star system. For the entirety of human history, we operated under a reasonable assumption that the space between stellar systems was essentially uncrossable on any practical timescale, and that our solar system existed as a gravitationally sealed environment. Objects within it stayed within it. Objects outside it stayed outside it. That assumption dissolved in 2017 with the detection of Oumuamua, a bizarrely elongated object that became the first recognized interstellar visitor in recorded history. But Oumuamua was deeply frustrating. It was detected only after it had already completed its closest solar approach and was accelerating back out of the system. It showed no cometary activity, emitted no gas, and left behind more questions than answers, including a still unresolved debate about whether its anomalous acceleration could be explained by known physics or required a more exotic explanation. Then, in August 2019, an amateur astronomer in Crimea named Gennady Borisov detected a faint smudge of light moving against the stellar background. This was 2I Borisov, and unlike its predecessor, it left absolutely no ambiguity about its nature. 2I Borisov was a fully active comet. As it fell toward the sun at approximately 100,000 miles per hour, solar heating caused it to sublimate vigorously, releasing a sprawling tail of gas and dust thousands of miles long. Its trajectory was hyperbolic, moving with far too much velocity to be gravitationally bound to our sunday. It had arrived from the interstellar medium and was passing through on a one-way trajectory, destined to return to the dark between the stars. The breakthrough was not merely in identifying its origin, but in what its cometary activity made possible. Because 2I Borisov was actively outgassing, astronomers could apply spectroscopic analysis to directly sample its chemical composition. For the first time in history, we were able to characterize the frozen material of an object formed around an entirely different star. The results revealed unusually high concentrations of carbon monoxide, significantly higher than typically found in comets native to our own Oort cloud, suggesting that 2I Borisov formed in the frigid outer regions of a very different type of stellar system, likely a red dwarf, before being ejected into the interstellar medium by the gravitational influence of a passing giant planet. The broader implication of 2I Borisov is one that alters our perception of the galaxy itself. If two interstellar objects were detected within a single 2-year window using the limited survey technology we currently operate, the statistical mathematics suggests the interstellar medium is saturated with such bodies. There are likely thousands of rogue objects from other star systems passing through our solar system. At this very moment, frozen remnants of alien worlds, debris from systems that may no longer exist, silent messengers from elsewhere in the galaxy. Our solar system is not sealed. We are perpetually immersed in a quiet, constant blizzard of interstellar material. Number 2. Entering the sun's atmosphere. Our sun contains 99.8% of all the mass in the solar system. It is essentially a sustained thermonuclear detonation held together only by its own colossal self-gravity. And for generations, it presented physicists with a problem that appeared to violate the foundational principles of thermodynamics. The photosphere, the visible surface of the sun, burns at roughly 10,000 degrees Fahrenheit. Yet the corona, the outer atmospheric layer that extends millions of miles above it, reaches temperatures of 2 to 3 million degrees Fahrenheit. The temperature increases as you move away from the energy source. This is physically backwards. It is the rough equivalent of stepping back from a campfire and finding that the air a kilometer away is thousands of times hotter than the flames themselves. The coronal heating problem had persisted unresolved for decades. To make progress, NASA concluded that direct investigation was the only meaningful path forward. In 2018, they launched the Parker Solar Probe with a mission to travel closer to the sun than any human-made object had previously ventured. The thermal engineering involved is remarkable. A 5-inch carbon composite heat shield serves as the probe's primary protection, its sunward face reaching temperatures of approximately 2,500 degrees Fahrenheit and glowing a brilliant cherry red, while the scientific instruments positioned just inches behind it in the shield's shadow operate at comfortable room temperature. In December 2021, the Parker Solar Probe crossed the Alfvén critical surface, the defined boundary of the solar corona. It entered the sun's atmosphere. It touched the sunday. Within that environment, the sun's gravitational field accelerated the probe to speeds exceeding 430,000 miles per hour, making it the fastest object ever constructed by our species. At that velocity, a journey from New York to Tokyo would take under a minute. What Parker transmitted back reshaped our understanding of solar physics. The imagery revealed magnetic switchbacks, sudden, violent reversals in the direction of the sun's magnetic field, snapping through the plasma like cracking whips. The probe flew directly through coronal mass ejections, with billions of tons of radioactive plasma washing across its camera systems. These observations allowed scientists to trace the acceleration of the high-speed solar wind back to specific magnetic funnels rooted in the solar surface, a significant step toward resolving the coronal heating mystery. But the deeper significance is philosophical. We constructed a fragile machine, sent it into the most hostile environment our solar system contains, and it looked back at us from inside the inferno. Number 1. Seeing the beginning of time. Every generation of telescope has expanded our understanding of the universe's true scale and consistently revealed that what we thought we were seeing was only a fraction of what was actually there. When the Hubble Space Telescope stared at an apparently empty region of sky in the 1990s and resolved thousands of previously invisible galaxies, it fundamentally altered our sense of the cosmos. But Hubble operated in visible and ultraviolet light, and it faced a hard physical limitation. The most ancient, distant galaxies in the universe, those from the first billion years after the Big Bang, are receding from us at such speed that the light they emitted billions of years ago has been stretched through cosmic expansion far beyond the visible spectrum and into the infrared. Hubble simply could not see them,